Hello, hello, hello. Welcome back to STEM Online Academy. My name is Jason Masterakos. I'm the founder and president of STEM Online Academy. All right, we're going to be looking at something interesting, right? So, lots of students usually treat uh, convergence tests like it's just, you know, a random mathematical weapon, you can say, right? Or tool, if you want, right? But strong students, right, first ask the question, what kind of infinity am I looking at? Right? What type of infinity am I looking at when I'm looking at this series? Okay, there's different types of infinities in mathematics. Okay, so the questions we're going to ask and answer today, I'm going to ask and answer three of them. I want you to do two of them yourselves because for those of you who know me, um, this is a channel where I want you, the audience, to think. Okay, I'm training. I'm trying to train future engineers, mathematicians, and physicists for the future. Right. So here are the questions. Okay, what does it mean for right an infinite process to have a finite result? What does it mean? Okay. Number two. I want you to think about number one. Okay. Number two. Why can infinitely many positive terms still produce a finite number? Okay. Why? Why can infinitely many positive terms produce a finite number? Right? That's a very good question. I thought about these questions deeply. Okay. Number three. Why is comparisons right? Right? Why is a comparison often more powerful than computation? Okay. So then again, why is it comparison? And when I mean comparison, I mean like why is a comparison test? I need to be specific because we are talking mathematically. Okay, so we need to be precise. Why is a comparison test more powerful than just doing a computation of a series? Okay. And number four, what does a convergence test actually prove? Right? What does it prove? Okay. I want you to think about that. And number five, right? Why do students, right? Why do students misuse ratio, comparison, and alternating tests? I'm going to try and answer as many of these as possible. And I may decide one or two for you guys to answer. Okay. Also, to make this really interesting, I put a really nice video on the side of what we're dealing with today. All right. So I hope you guys will enjoy the video. I like to make mathematics visual, right? Because I feel like just me, writing on the board, solving the problems, is going to bore you guys unless I give you entertainment and I actually provide a serious amount of value for you guys. Okay, so let's go ahead and look at this video. Okay. Okay, so what you can see here, right? Series and sequence, right? So you see that we have a sequence, a subscript n equals 1 over n. Okay, that's your typical sequence, the basic sequence. And we're dealing with a harmonic, some sort of a harmonic trap. Okay, so as you can see here, right, we're comparing a geometric series with a harmonic series, and we can see that the total of the geometric series will converge to 1. Okay, now if it converges to 1, that means that the limit, right, the limit should equal 1. Okay, all right, and you can see a lot of interesting stuff happen here, right? Okay, when it comes to sequences and series, right? If a subscript n goes to 0, does the summation of a subscript n, where a subscript n is a sequence, converge, right? Not necessarily. It would actually diverge, right? Like the p-test, right? Okay, because the limit as n approaches infinity, right? 1 over n, okay, would equal to 0, and by that, there's a series test that states that that should imply that it's going to diverge, that the sequence would diverge. Okay. I'm going to leave this on and I'm going to start answering the questions, right? So, because it's highly relevant. Okay, right? So let's continue. I'm going to replay it. So that's why you can make sense of what I'm saying here. So, what does it mean for an infinite process to have a finite result? What does that mean? So, think about it. What does it mean for it to have a finite result? All it means, right, is that the terms, right, because we're dealing with sequence and series, so we have terms that are being added, okay, they're going to shrink, they're going to approach zero, okay, that is what's happening, and they're going to approach zero fast, okay, so as we're adding up these terms, right, in our sequence or series, right, as we're adding up these terms, right, they're going to approach zero fast, okay, that's the reason why, right? Why there's an if why you can have an infinite series producing a finite result. Okay, so for instance, a geometric series is an infinite series. Quite often, it should have a finite result. Okay, no dispute there. All right. Now, question two: why can infinitely many positive terms still, right? Infinitely many positive terms still have a finite number. Don't get confused by from question one to question two. I want you to be very careful. There's a difference, right? Just give me a sec to rewind. Okay, there you go. Right? So, for question two, why can infinitely many positive terms still have a finite number? Okay? The reason for that is because of the fact that the numbers, right, are just shrinking in size very fast. Okay? That's what's happening. As the numbers shrink in size fast, right? The positive terms, we're talking specifically about the positive terms, as they're shrinking in size fast, right? They're outpacing, right? They would have to outpace these new terms. Okay. Does that make sense? I want you to think about that. Think about what I'm saying here. Okay. Rewind you a bit. This video goes fast. Let me know if you guys like the video. It will be handy to say something in the chat. Or if you have any disputes of any of the conceptual answers I'm giving to these questions. Okay. I always like to talk to people. Talking creates thinking. Okay. Back and forth dialogue. All right. So, yes, that's the reason why, right? It's because of the fact that the numbers are shrinking in size fast, right? And as they're shrinking in size fast, they're going to outpace the new terms. And as they outpace the new terms, that's why you can have infinitely many positive terms adding to finite number. Somewhat related to question one, but question two, I feel like is slightly different because we're talking specifically about positive terms, right? This one's sick. There we go. All right, so question three. Um, why is comparison often more important than computation when it comes to convergence or divergence of series and sequences? The reason for that is calculating a summation, right? You calculate the summation. Let's say you want to calculate the infinite series of, let's say, a geometric series, like what I have on the video there, right? You can calculate it. It'll give you a finite result, right? Infinite series will give you a finite result mathematically. However, though, that finite result doesn't doesn't tell us if the series is converging or diverging. You understand what I mean? So calculating that infinite series doesn't tell us anything in terms of the convergence or divergence of the series. Okay? It tells us other things that are very important. I'm not saying it's not important, but computationally wise, no. Um, that's where convergence, certain types of convergence tests are more important. For one, since we're talking about comparing computation to um, comparison, right? The comparison test, right, will tell you if a series is converging or diverging, right? So a comparison test, for instance, you'd have to, let's say you have And quite often you'd use it on, let's say, a fractional sequence. You're taking the infinite series of some sort of long fractional sequence, for instance, right? All right. So let's say n squared plus 1 all over n cubed plus n squared plus 2n, whatever the hell it is. Okay. Now that can look intimidating, but the reason why the comparison test is better than just pure calculation when it comes to convergence, determining convergence or divergence, not just because the fact that a comparison test tells you whether it converges or diverges, as opposed to just calculating a series, but also because of the fact that um, you can easily bound a complicated series like the one I mentioned, n squared plus 1 all over n cubed plus n squared plus 2 and whatever. Okay, you can easily bound it. So you would want to, for instance, take an upper bound on a complicated series like that, right? And come up with a new sequence, right? So for instance, let's say our a sub n was n squared plus 1 over n cubed plus n squared plus 2n. That's our a sub n. Our b sub n would more likely be something, let's say, of the 1 over n type. Okay? All right? Don't ask how I got to that, but I'm going to explain that. I expect you guys to know a bit more on series. If you have any questions, put in chat below. But I can get the point is, I can get a very complicated series sequence situation, and I can easily make it much simpler to evaluate because then I have the mathematical tools of convergence tests that I can use. I know that the summation now of 1 over n as n equals 0 to infinity. If I use another type of convergence test, right? It's very easy to show that it diverges. Okay, shows that it diverges by a p-test, right? So as you can see from that, that's why a comparison test is more important, right? It makes the calculation simpler by creating an upper bound for a new sequence that's simpler than the original sequence of the series, and also because um, it's a type of convergence test for a calculation, isn't it? It's just, no, it doesn't work. Hope that makes sense. Okay. Number 4, what does a convergence test actually prove? I don't know if I should give this to you guys for homework. Okay. What does a convergence test actually prove? Well, if we were to articulate into more deeper in a deeper conversation, yes, it does tell us. It does prove either if the series is converging or diverging, right? That's what it tells us. But it also tells us something deeper, okay, about the terms. What does it mean for a series to converge or diverge? Okay, so I answered part of the question, but it's not entirely cohesive. Right, and I did that on purpose so I can engage with you guys. Your homework, right? I want you to actually go home and think about this more deeply, right? What does a convergence test actually prove? Okay, what does it prove? That's your homework. That's one of your homework. All right. I want you to struggle with it. It's not that hard. It's pretty basic. But I wanna develop an intellectual discussion with you guys. Okay, and then tell me in the chat. And another question. Before I get to another question, I want to bring up something about myself that is very important. Okay, especially for those of you who are in university, and because I know I have an audience. I have an audience of people. There's people who are very fast at math and they get everything, and it's not just math; they get everything really fast in general. Okay, and then there's another subset of you that are struggling deeply. Okay, and I want to let you know that that's okay. I was there at one point in my life too. Okay, when I was well, for me, not in university, but it was in grade 7 through 9. Um, I was struggling with mathematics deeply, really badly, actually. Okay. until I had these two teachers that not only changed my life, but probably even saved it. Okay. One in grade 8 and one in grade 9. It was by the end of grade 9, uh, I was still having trouble. It took two teachers to practically, I won't say bail me out, but show me how to think about mathematics the correct way. It's not the fact that I couldn't do mathematics or I wasn't smart enough or people think you need to be a genius to do advanced mathematics. I think that's baloney. Um, but what it is that you need to have a system. Yes. Yes, you need to have a system. I'm looking directly at you guys. And I'm looking directly at you guys because a lot of you think that you can do mathematics algorithmically. And it's not your fault, it's your teacher's fault. Okay? They're giving you mathematical questions, I don't know if we can call them mathematical questions, that are routine and algorithmic. For instance, I want you to, let's say you have y equals mx plus b. Graph y equals x. Okay, that's one question. And they'll give you this for homework. Then graph y equals x plus 1, right? Question 2. Question 3, graph y equals x plus 3. How does that teach anybody anything? Once you figure out the graph y equals x, you need to move on to a much more complicated question. You learn through difficulty. You don't learn from doing repetitive nonsense. Okay? All right? That's my message. Okay? And those teachers in grade 8s and 9, they taught me that because I remember they were hard teachers, but they set me up for success. Okay? Uh, and I remember because the questions that they gave me in homework were not like any of the teachers that I had even in high school, and they were junior high school teachers. Okay, they would change up the questions, and I knew that my way of doing math, I wasn't learning math. I was learning a formulaic way of doing math. It was artificial, and it's not good, right? So you need to develop a system that helps. For me, it came to me in grade 10. Well, it started with them. They told me that I have to start getting into the thing of developing a strategy of solving problems, right? For me, I invented something called the systems technique. Not when I was with those teachers, I was doing bad with them. But I was asking in grade 9, and in grade 9, this my high school teacher, what can I do to improve? And he says, develop a problem solving method. Right? A problem solving method in which you can use your logic to solve problems, right? Step by step way for you to do it. Okay. And for me, that's the systems technique. Okay. It's visualize. Okay. Step one is you visualize what's going on. Quite often in mathematics, especially if you do problem solving questions, geometry questions, graphing questions, this makes the most sense. Okay. So you want to be able to visualize what's happening. Okay. And when I mean visualize, it doesn't always have to mean graph or model, but be able to, it may be even an abstract equation. How would visualization work there? That's a very good question, maybe one of you might ask, right? If you have an abstract, serious question. What I mean by visualize, interpret the language correctly, understand what it's asking, whether it's an abstract equation or a big word problem. But make sure you understand what's being asked, okay? So you do that linguistically, an abstract problem, equation, if it's just equation, or if it's a problem solving question in a graph, you want to actually draw it out in detail and assign quantities and variables that will make you help and understand the problem. Okay, so that's visualize, step one. Step two is you want to model. Okay, I don't mean model like you're a model. That meant to be a joke. Like modeling like women. No, that's not what I'm talking about. So what I mean by model is come up with the things that you know and don't know, right? From step one, the things that you don't know and don't know. List all the important things and try to create a semantic map of how you're going to do it, how you're going to solve the problem. Okay, so that's step two. Step three, you want to execute. You have your graph, or you graph or whatever. Let's say design or whatever it is that you're dealing with. Okay. You have a model, your plan of attack. Well, let me say plan of attack. You can say a plan of attack. Um, and how to deal with the problem. Okay. You list your knowns and unknowns, right? And then you're going into the execution phase of step three. Execution means doing the algebra, right? That's the somewhat of an easy part, okay? Like algebraically translating from the visualization to the algebra, right? However, setting up a model is not easy, okay? That's what people have the most difficulty when it comes to mathematics is setting the problem up. And a hard problem will do that. Now, a regurgitation question algorithmically will not do that. It will just be pure nonsense, right? And a lot of these teachers are doing that. They keep giving you those types of problems. That's not good. Okay. And step four, you want to be able to execute. Like, what is? I mean, verify. Sorry. What does verify mean? Prove that the left-hand side and right-hand side of your solution is correct. So you don't want to just submit it and say, "Oh, I calculated something." You want to make sure that it makes sense with reality. Okay. Because without mathematical reality, more likely what you're doing is nonsense. And if you can't verify it, then more likely the question is nonsense too. Okay? All right. So this system that I created for myself has helped me get through high school. Not just get through high school, do very well. And then from high school, so my mathematical journey improved tremendously. Okay? Then from there, from high school, I decided to take mathematics and physics in university. It's a double major. Went to Carleton University. I finished in 6 years. It was a long degree. It was a double degree. And I finished with a 3.85 GPA. All right. So, and from that point on, I had two options. I said I could either go to graduate school, but graduate school is just, it's just, I could have gone, like I have the grades and everything. But the thing is, it was already a very long and very hard degree, right? And I didn't want to put more of my brain cells getting exhausted. So that's what made me think, how can maybe I can start a coaching slash tutoring company. That led me to be the founder of Semiline Academy, where I plan to improve, right? Uh, our goals and slash philosophy is to dramatically improve university students when it comes to mathematics and physics courses, specifically calculus, physics, and proof-based courses, right? When it comes to midterms and exams, I want to show them that they don't have to struggle, that they can actually improve tremendously with my technique. Okay, and I want to share the beauty of math with you guys. Okay, right. So that's what led me to be the founder of STEM Online. Okay. All right, and then let's get back to the last question. Why do students misuse ratio, root comparison, and alternating tests? Uh, well, I want you to answer that. You, the student, after everything I've said today, tell me why you think you are misusing these tests, right? Why are you misusing them? I want you to answer that. Tell me what you think, okay? Let me know in the chat below, okay? So that is it for today's video. Before I get going, um, if you watched my the other screen, really cool Magnum simulation of what we were talking about. Uh, I'm gonna let me just here's my systems technique: visualize the model to execute to verify. I also want here's another homework question. I want you to use my system to solving a mathematical problem, whatever that math problem is. Okay, use it. Okay, break down the problem. Deep breathe. Right. Actually, I want you not to be anxious. Do the problem right with a clear mind and use this technique. Okay, and I can guarantee you will see results. All right. So before I get going, if you don't know or understand my systems technique uh, in more detail, because I'm sure you got questions like I don't see how this is working, whatever, or I don't get it, or whatever it is, I left the free PDF. It's completely free for you to download. Okay. Um, should be in this video. If it's not, just click on one of the other videos. All my other videos have it. But if not this one, because this one usually will have a sum of all the links. I don't know if it has the separate PDF. I'm gonna check that. But there is a free PDF somewhere where I go through the most common um, traps when it comes to calculus courses, specific hard calculus courses, where this would be handy. Especially in analytic, when you have to use analytic geometry and stuff like that, and calculus problems, tangent lines, stuff like that, where this is really handy for advanced mathematics. Okay, and if for A or B reason, you, because not all of you are exactly the same, but some of you may be taking a calculus course and you're having trouble understanding the logic, right? You may be having trouble understanding the logic behind calculus. Because not every calculus class is the same at every university. Okay? You're maybe you're a gifted student and you really want to accelerate your math and you have an interest in mathematics for the sake of it. And you plan to, or you just want to study in university. And you want to understand the reason of how things are derived, how to think mathematically, how to think as a systems thinker, then, or like I said, a university student who's having trouble with the logic and the systems, you may want to get my new book, Axioms, right? And Axioms, right, is a book tailored, right, to teach you to become uh, highly equipped logically, right? In mathematics, learning the systems, learning the techniques uh, of how to do mathematical proofs, but not just for mathematical proofs. So it's going to help a lot in your courses, that's sure, but it's also going to help you in your life. Mathematical thinking is not just for a course. Okay, I know a lot of you want to just strive for A's, which is good. It's very good. I'm not saying not do that. Don't do that. But there's much more important things in life, not just getting that A in that course. Okay, and learning to think mathematically will say actually can save your life. Trust me, to make the right decision, to be logical and all that. Right. So this book does it. Right. Axioms will help you think mathematically. Okay. Again, thanks for watching the video. Like and subscribe. It helps the channel. Again, next week there'll be two videos. Every week is two videos. Catch me on Tuesdays and Sundays. And again, I want to say like and subscribe. Thank you for the subscribers I already have. You're a tremendous help. Um, Absolutely tremendous. And I want you guys to continue to watch my videos and be a part of the STEM Online family. Thanks again, guys, and have a great end of Sunday. See you next time.